This section provides the SQL for how to calculate likelihood ratios. This brief presentation was organized by Dr. Alemi and narrated by Yara Alemi. Suppose that we want to predict patients' odds of mortality from patient diagnosis. We can use naive Bayes to make these predictions. However, to do so, we need to calculate the likelihood ratios associated with each diagnosis. Since there are thousands of diagnoses available in the electronic health record, one has to find a simple procedure for calculating these likelihood ratios. It would be difficult to do this using logistic regression or other statistical tools, so this section walks you through an SQL code for doing this with electronic health records. Under the assumption of independence, we can calculate the likelihood ratio associated with each diagnosis as the ratio of prevalence of the diagnosis among dead and alive patients. 4 counts are needed: the number dead and the number with the diagnosis among dead, the number alive, and the number with the diagnosis among alive. Next, we will show how these counts are calculated in the SQL code. Recall that the likelihood ratio is not defined when we are dividing by 0 or when the ratio is 0. So the SQL code shows us how to avoid these situations. In the following SQL, we do not show all of the code. The code for cleaning the data and removing duplicates is not shown. Some intermediate steps also may not be shown. You should use the attached code to understand the ideas and not just simply regurgitate this exact code for your assignments. The first step is to split the data into training and validation sets. Note in this code the random number generator needs a seed that is different for each person. Hence we use a patient's ID as the seed. Since the seed needs to be a number, we generate new ID and cast it as a binary variable. We randomly select 80% of cases for training, and the remainder we set aside for validation. The likelihood ratios are estimated from the training data and then cross-validated on the 20% of data that we set aside. In these steps here, we are checking to see if the patient has died within 6 months of the diagnosis. For patients who have not died at all or whose date of death is null, we assign 0, indicating that the patient has not died within 6 months. Next, for patients whose date of diagnosis, here shown as date of admission, is within 182 days of the date of the last encounter, we assign a null value. We do not have a 6-month follow-up period for these patients, and therefore we cannot use their information. Finally, if the admit date and date of death are within 182 days of each other, then we assign a 1, and we name this variable dead within 182 days, or dead 182. Note that we generate this data from the training set. We select from our cohort the cases that have the same ID as the training set of data. We get the diagnoses from the inpatient encounter file. This code assumes that you have removed duplicate diagnoses within the encounter file. Otherwise, this join will result in many duplicates. In this step, we count the number of times the diagnosis co-occurs with death in 182 days. The analysis is done for repetition of each diagnosis. We have not shown how the repetition variable is organized in these slides, as an earlier introduction to rank function describes this process. Here, the group by command allows us to count for each diagnosis and its repetition a separate set of statistics. We are also ignoring any diagnosis that does not repeat in at least 29 distinct patients. For each repeated diagnosis, we calculate the number of times the diagnosis occurred among dead patients and among alive patients. Keep in mind that these sums will not be accurate if we have not previously removed duplicate IDs and duplicate diagnosis codes for the same person. We can show what we have calculated as cell values in a contingency table. The rows indicate whether the repeated diagnosis is present or absent, and the columns indicate if the patient has died within 182 days. Using the contingency table, we can see that number dead with repeated diagnosis is the cell value shown as A, and the number alive with repeated diagnosis is the cell value shown as B. So far then, we have calculated two cell values in our contingency table. The remaining cell values can be calculated from the difference between our calculated cell values and our total values. For example, the patients who do not have a repeated diagnosis and are dead in 182 days, i.e. C in the table, can be calculated by our estimate for A and the total dead. Remember to make sure that total dead is calculated for distinct patients and does not include duplicates. In the steps shown here, we calculate the likelihood ratio for each repeated diagnosis. First, we calculate the totals. We start by declaring the totals as integer constants. Second, total dead is calculated where dead 182 is 1. Note that this count is for distinct patient IDs. Third, total alive is calculated where dead 182 is 0. This count is again for distinct patient IDs. Now we are finally ready to calculate our likelihood ratios. But first, we have to make sure that our SQL can circumvent potential hangups due to division by zero or other similar errors. In the first line here, we are saying that if there are no patients with the diagnosis who died in 182 days, then calculate the likelihood ratio as 1 divided by 1 plus the total number of patients with the diagnosis. This guarantees us a number that is as close to 0 as possible while still being proportional to the sample size. Next, we take care of the situation where all of the patients with the diagnosis are alive. In this situation, the likelihood ratio is calculated as 1 plus the number of cases with the diagnosis. Finally, we calculate the likelihood ratio as the proportion of dead people who have had the diagnosis divided by the proportion of alive people who have had the same diagnosis. Note that for these calculations to work, we need to cast all integer values into floats. These slides have shown the ideas behind how SQL can be used to calculate the likelihood ratios for large numbers of predictors. Thank you for listening.